We are going to go over a rotation equilibrium question. A force of 2.2 Newton acts tangentially to the rim of a solid 52 kg disk that has a radius of 32 centimeters. How long does it take to accelerate the disk from rest to 210 revolutions per minute? Now the first thing is, let's convert first the final velocity we've been given to radians per second. So omega final is 210 revolutions per minute, and do multiply that with, we know that in 1 minute we have got 60 seconds, and also we know that in one revolution we have got 2 pi radians. So just multiply 210 by 2 pi and then divide by 60, giving us 21.9911. This is going to be now radians per second. So whenever a force acts making perpendicular or making 90 degrees with a certain displacement, for example, you have got this displacement and then a force acts 90 degrees to this surface. Say the distance here is d, and then there's a force which makes 90 degrees to this surface f. This is going to produce a turning effect, and that is called torque. And so we find that torque is simply equal to force multiplied by the perpendicular distance. In this case, it's the radius. We also know from Newton's second law of motion that force is mass times acceleration. In this case, torque, which is the equivalent for force, is moment of inertia, which is the equivalent for mass, and angular acceleration, which is the equivalent for linear acceleration. So therefore we find that moment of inertia times angular acceleration is going to be equal to force multiplied by the radius, giving us angular acceleration being equal to force multiplied by the radius divided by the moment of inertia. Now this is a solid disk. The moment of inertia is half mr squared, and so this will give us, now we have got a 1 here, 1 over 1 over 2. This is going to give us a 2. This r will cancel with 1 r down, so that will be 2f, and then divided by mass times radius. Therefore the angular acceleration is going to be equal to 2 multiplied by the force, which is 2.2, and then divided by the mass, which is 52, multiplied by the radius, which is 0.32 in meters. Just divide the 32 by 100. So 2 multiplied by 2.2 divided by 52 multiplied by 0.32. The angular acceleration is going to give us 0.2644. This is in radians per second squared. Now to find the time, final angular speed is equal to initial angular speed plus angular acceleration times time. Angular speed, the final one, that is 21.9911 squared. That will be equal to, of course, the initial angular acceleration is 0, as we've been told it came from rest, plus the angular acceleration, which is 0.2644, and then times the time. Therefore the time is going to be 21.9911 squared divided by 0.2644. Let me just repeat that. 21.9911. Actually this one we don't put a squared. The one I was thinking of a squared is omega squared is equal to omega initial squared and then plus 2 alpha theta. So this is another formula here which is different from the one which I've used. The one I've used is V is equal to U plus AT. So it's not supposed to be a squared there. So it's just 21.99 and then divided by 0.2644, and that is going to give us 83.17 seconds. So that is the time then. Now question B. We've been told through how many revolutions does it rotate during this time. So during the time that we've been given, we know that distance is equal to ut plus half at squared. And the distance in angular terms is theta, and that will be equal to, the initial here is 0 because it came from rest, so it will be just half angular acceleration times time squared. So theta is going to be equal to half the angular acceleration, that is 0.2644, and then the time we found 83.17. This is also squared, so we just punch what we have there. So theta is giving me 914.5394841, and this is in radians, but we want in revolutions, so we're going to convert this to revolutions. We know that in one revolution we have got 2 pi radians, so the radians and the radians cancels, therefore we're just going to divide the answer that we have here by 2 pi, and that is going to give us 145.55 revolutions. So therefore that is going to be the solution.